With equations of motion, these are the symbols that we use, which v is your final velocity, u your initial velocity. The final velocity and initial velocity can both be equal to 0 if an object ends at rest or starts at rest. You've then got displacement, which we symbolize with an S, but sometimes you might see it in books or something symbolized with an X. That's okay. Time with a T, and acceleration with an A. In order to use the equations of motion, you have to use the SI units. So it's going to always be meters per second for velocities. Displacement needs to be in meters, time in seconds, and acceleration in meters per second squared. You've then got a situation where a couple of little heads up, if you're using this equation of motion over here, very often you can land up in a situation with a quadratic equation. And when that happens, you may want to use one of the other equations of motion to get a piece of information and then substitute into one of these equations in order, kind of do it in two steps, because once you get a quadratic, a few people will find the quadratic absolutely fine, but once you get a quadratic, often it looks quite difficult if you're trying to solve for time. So sometimes you first get, let's say, the final velocity of v squared plus equals u squared plus 2as, substitute the v in over there, and then work out the time from that equation. Don't forget that if acceleration is, if an object is in free fall, so if we're dealing with free fall, then acceleration is always 9,8 meters per second squared downwards. Don't forget that direction is always important in the equations of motion, and that you get those right. They sometimes ask you to, you get given information in kilometers per hour, and you will recall that if you've got kilometers per hour, you know exactly how to change that into meters per second, and you're going to often need to do that with an equation of motion. Remember also in these questions that they often talk to you about a reaction time. When you're in a reaction time, so for example, let's say a cop is standing still while a car moves past at, let's say, 50 meters per second. It takes the cop 2 seconds to react. Before I go into an equation of motion about anything, and this guy is, let's say, going at a constant velocity. So he's going at 50 meters per second, and it's a constant velocity, but the cop is going to accelerate once he starts going. Once he starts going, he's going to accelerate at, let's say, 5 meters per second squared. How are we going to find out when he, let's say he does that for 10 seconds. Let's just write that in. What you've got is you've now got an object that's moving at a constant velocity, and that will be, so if that's happening for 10 seconds, then we can work out how far apart they are, let's say, at the end. So the first thing is that the car will have made some progress. So it's at constant velocity, so I can say distance is equal to, first it took 2 seconds to react, 2 times 50. That's the first part of the distance. And then it carries on for another 10 seconds, so I can actually say 12 times 50 over there, and I can land up with 600 meters. So the car has moved 600 meters, the cop hasn't done anything, and then he's going to accelerate from rest. So S is going to be equal to ut plus a half at squared. What's important to differentiate is that the car has moved at a constant velocity, so we use the simple equation of motion, S is equal to v times t. But the cop is moving at a certain acceleration, so his initial velocity is 0. What is his time? He goes for 10 seconds, a half, his acceleration is 5, 10, and we land up with the fact that he will only have, by that stage, traveled about 25 meters. that means that there is still 575 meters between them. So those are the kinds of things that you can expect. You need to be aware of reaction times and know that you need to do them a little bit separately. You need to be aware of starting and ending as well at rest, and therefore you get a 0 meters per second for either the initial or the final velocity. You need to know how to move from meters per second into kilometers per hour, and you need to know that gravitational acceleration is your 9,8 meters per second squared. Let's just try one more type of example. Let's say I drop an object from a height of h. Now, what is its velocity when its velocity when it hits the ground is v? Let's say instead of dropping it from h, let's just make h a bit smaller. That's nothing. Instead of dropping it from h, I drop it from twice the height. What is this velocity's two relationships with velocity 1? So we need to find an equation of motion that's going to help us with that. Remember, both objects are going to start at rest. And we need the final velocity, we need distance, and we know the gravitational acceleration is going to be 9,8, and so the a is going to be exactly constant. So let's see what happens. My first story, v1 squared, is equal to u squared, which is 0, so we can make it disappear, plus 2ah. What happens if I rearrange that so that well, let's first do it over here. So the second velocity is equal to 2a, and don't forget that has to be squared. Again, it starts at 0, so u gets cancelled out. So it's 2a, and it is 2h. So now I am landing up with 4ah, which means that it is double the old value. This 2ah, it's 2 times 2ah. If I now say that therefore that's equal to twice v1 squared, we now need to get a relationship between v1 and v2. And because of the squaring function, it's going to be the square root of 2 that is going to be the factor difference. So in other words, the second velocity is going to be the square root of 2 bigger than the first velocity.